Today's webinar, as John has pointed out, is on how to select a flow meter, and there's 8 sections to that, which I'll just briefly go over just now. I'm going to talk about the premise of the presentation and introduction, and I'll talk about the kind of flow meters that we'll be talking about. The general considerations about flow measurement: do you really need to? How important is it? Can you do it? And then obviously very important to selecting a flow meter is the process conditions: pressure, temperature, fluid, etc. There's then a section on information, meter information, and that's how the process conditions guide us towards choosing a meter. And then we'll talk a little bit about physical conditions, or I could equally have put down there ambient or environmental conditions. The penultimate section is on additional equipment, and this is where sometimes things get a bit complex and a bit costly. Very often, as we'll find out, it takes a lot more than just a flow meter to measure flow. And then we'll finish off in terms of me speaking or presenting with a couple of case studies. And then hopefully, if I don't waffle too much and stick to the script, we'll have time at the end for some attendee submitted questions. So, as an introduction, there are many applications in many industries that require flow to be measured. Now, we commonly think of things like, oil and gas or water, or, more contemporary carbon dioxide and hydrogen as examples, ammonia, fuel measurements. But there's also, other things, beer in a beer factory, paint in a paint factory, cooling water to some sort of reactor. So there's many areas in which fluid flow measurement is very important, and therefore the selection of the flow meter is very important. And each of these measurements will have their own specific criteria. They may be benign fluids, they may be really dangerous fluids, they may be at atmospheric pressure type temperatures, they could be extremely high pressures and temperatures, and all of that has to be considered. And probably one of the most significant ones, certainly not in terms of safety, but definitely in terms of measurement, is the uncertainty or the accuracy requirement. Do you require a very accurate, i.e. low uncertainty measurement, or are you happy with a kind of indication, low accuracy, high uncertainty type measurement? So when we're going to select a meter, it's these criteria, the pressure, the temperature, the fluid, and the measurement uncertainty requirements that we bear in mind as we try to guide ourselves towards selecting the best meter. Although we'll find out during the presentation, there's rarely such a thing as the best meter. As I'll hopefully make clear throughout this presentation, it's actually pretty difficult or it can be very difficult to select the correct meter for a particular application. Not always. Sometimes it's quite straightforward, but more often than not, unfortunately, it can be quite challenging. So it's important that the person who's making the selection, along with his team, his colleagues, and his vendors, understand the basics of how each technology works. For example, on the right-hand side there, we have a SEEK multipath ultrasonic flow meter. You have to know the advantages and drawbacks of each type of meter, and I'll talk about some of these later. And also, because these things are generally commercial and generally have a budget, you have to be able to justify any choices that you make, any selections you make to your management, to your project team, to your finance manager. So not always as easy as it sounds. Very often measurement is a lot more expensive than non-measurement people think it will be. Now, I think it's fair to say that there are dozens of meter types on the market. However, in the current day, some are more popular than others. And the sort of meters that we'll be talking about today are traditional meters, if you like, turbine meters and differential pressure meters, cone, venturi, orifice. and also some more modern type technologies, ultrasonic Coriolis electromagnetic meters. There are other meters, PD meters, wedge meters, but the majority of measurement done in industry these days is done by one of the meters or one or more types of the meters on the screen. So, general considerations before we go and start writing checks for meters or even selecting a meter. There's a few questions that need to be asked. The big point there, right in the center of the diagram, is: do you need to measure the flow? And this may sound like a really silly thing to say, but if you don't need to measure the flow, well, don't measure it. There might be another way you can measure the flow. You can maybe infer the flow. But let's assume that you do need to measure the flow or would like to measure the flow. Another thing you have to ask is, can you measure the flow? Is there room there for a meter? Are you going to have to redesign your plant in order to fit a measurement in? And very often that is indeed the case. And then assuming we can and we need to, the next 2 points kind of lead on to each other. Why do you need to measure the flow? Is this just for a process indication, for example? So you'd be happy with a high uncertainty or low accuracy meter, or is it a really critical measurement? Is it, for example, safety critical? I'm guessing here water to a nuclear reactor, or a custody transfer of an expensive fluid like hydrogen or sequestered carbon dioxide. And if that's the case, then that also impacts how accurately you need to measure the flow. In a case like that, for a safety critical measurement or a $10 million oil offload, you would probably need to spend more money in measurement because you want to measure the flow with a lower uncertainty. Just presenter's golden rule has been broken there, folks. Just putting my phone on silent. So we've decided that we do need to measure the flow and that we can measure the flow. And also we know, whether it's by commercial agreement or by legal requirement or by process optimization decision, we know what uncertainty in measurement we require. Well, where do we go from here? First thing I would do in this situation, and I have been in this situation many times, is look at the process conditions. First and foremost probably is the fluid. Is it a liquid? Is it a gas? Is it a wet gas, which is a two-phase fluid? Is it a multi-phase, three-phase fluid, oil, gas and water? And that can, multi-phase can equally apply to something like CCUS. Is it perhaps even a four-phase fluid where it has solids entrained, coming from a wellhead? So the fluid, the nature of the fluid is a very important primary consideration. The flow range, the pressure and the temperature are also very important. Now, the flow range can vary dramatically. For example, the minimum flow that you want to measure, or the maximum flow, that you want to measure, may be 3 times larger than the minimum flow you want to measure. And we call that a turn-down ratio of 3:1. But it's equally possible that the maximum flow you want to measure is 30 or 300 times larger than the minimum flow you want to measure. So that really impacts on the type of meter and the number of meters that you want to consider. The pressure and temperature, again, of course, that affects not only the meter type, but the materials, for example. Measuring, clean water at 2 bar and 20 degrees C is completely different from measuring, say, sour natural gas at 400 bar and 80 degrees C. So the pressure and temperature, along with the flow range, are primary considerations, along with the fluid, the nature of the fluid, the phase of the fluid. The density range and the viscosity range are also very important because they tie in with the Reynolds number. Now, I'll make an assumption here that the people dialed in know a little bit about, or a lot about, Reynolds number. Basically, it describes how the fluid is moving through the pipe, and there are three regions of Reynolds number. There is the turbulent, high Reynolds number, and that's probably the easiest area to measure in. There is the laminar, very low Reynolds number, which is slightly more challenging, but again, it can be done. And then there's a transition range where the Reynolds number is between the turbulent and the laminar. And again, that is very important. There are some meters which just cannot cope with Reynolds numbers in the transition range. So again, when we're doing our preliminary investigations, the viscosity and the density of the fluid are very important considerations, because they will give us information on the Reynolds number range. Also very important is the vapor pressure and the dew point, the point at which the phase changes from gas to liquid or liquid to gas. We don't want to, for example, try to measure a gas, but choose a meter which turns the gas to a liquid in the process of measuring it, or vice versa, choose a meter which is for liquid, but then select a meter which turns the liquid into a gas or causes gas breakout, the vapor pressure being breached. So again, the vapor pressure and dew point are considerations. We want to keep away from that if we can, and if we can't, we don't want to make that situation work by turning a single phase fluid into a two-phase fluid. And finally, on this section, this slide, is the nature of the fluid. Is the fluid benign like water, in which case there's not many meters can't cope with measuring water or air, for example? Or is it really corrosive and erosive? Is it a gas, for example, that has a high hydrogen sulfide content? There are certain meters that you just do not want to expose to that type of fluid, because they just won't last very long, they'll break down. And of course, when we talk about material selection, the corrosive, erosive properties and other properties of the fluid are paramount and should be in the forefront of your mind as you make the selection. So now that we've considered all these process conditions, that starts to at least point us in the right direction, about what attributes the required meter should have. Sensitivity to physical properties. If I have an extremely high H2S gas, I want to make sure I have a meter which doesn't have any components in the gas which are going to be corroded or eroded by the gas. The Reynolds number, again, we spoke about that. Now that we know what the fluid is, its pressure, temperature, density and viscosity, that will tell us where the Reynolds numbers are going to be, and depending on the answer to that, or the answer to that question, the Reynolds number range, that will take certain meters out of the equation straight away, and they'll be eliminated from any future consideration. But then the other meters that are still in the hunt, if you like, in the consideration, there are further things that we have to consider. The turn-down ratio, we mentioned this before. Is my maximum flow 3 times greater than my minimum, or 300 times greater? Some meter types have a turn-down ratio of 3:1 or 5:1. Some other meters, for example, ultrasonic meters, gas ultrasonic meters, have a turn-down ratio of 100:1, maybe even more, depending on how well they're calibrated. So again, that's a consideration. The turn-down ratio gives rise to the question, do we need more than one stream? And this is where things sometimes get a bit costly. On the right-hand side there's a graphic of a multi-stream gas ultrasonic metering skid. And the reason there are so many streams is quite straightforward. One meter cannot cope with both the minimum and the maximum flow. In this particular case, it takes 4 meters to measure from the minimum flow with only 1 meter operating to the maximum flow where 4 metering streams are open in order to be able to cope. Now, you can tell just by looking at that diagram that that's not cheap. That's maybe a lot more expensive than the finance manager, the picture he had in his mind when he told you to go and get a gas measurement solution in place. So again, very important. The pressure rating stands to reason. You know, you might be able to use thin wall carbon steel pipe for a water measurement at 2 or 3 bar. You're not going to get away with that if you have a gas which is at 150, 200 bar. You're going to have to get more sturdy and unfortunately more costly material. And then finally, I think for this slide is the material of construction, and that's again goes back to the process conditions. You know, normally we'd use something like carbon steel for a metering skid, you know, typically for for the oil and gas industry or the water industry. But if I have a corrosive fluid, I may have to make my skid out of something like stainless steel or duplex or Inconel. And at that point, the costs start to really, you know, you can put a 0 on the end of any thought you had of the overall cost. But if we want to do this properly and we want to do it most importantly safely, and that demands a more exotic material, well, that demands a more exotic material. We don't want to put anyone in danger in order to obtain a flow measurement. Final point for this, sorry, of course, I should know this. The units of measurement are absolutely critical. Do we want to measure the mass of the fluid? Do we want to measure the volume of the fluid, which would be corrected to a pressure and temperature? And again, that requires more instrumentation, which maybe wasn't considered initially. Or for natural gas systems and maybe hydrogen systems in the future, I'm not sure, it may be sensible to trade on energy. If I'm using hydrogen as a fuel or natural gas as a fuel, it's actually the amount of energy that I'm interested in, not necessarily the volume that energy occupies or the mass of that energy. That's probably less applicable to hydrogen because my understanding is that hydrogen will be very pure. So you could infer the energy from the volume or the mass. But for natural gas, it's very common to want to trade in energy. And as we'll see later on during the additional equipment section, that requires a lot of extra cost, equipment, and space. Okay, another thing we have to look at is where is the meter going to go? It could be in a desert in Saudi Arabia or a field in the UK or Germany or America or Canada or Australia. Conversely, it could be on a very, very small platform located very, very far offshore. Now, clearly, the space available to the selector of the meter or the metering system is very much different in these cases. So we have to look at things like the upstream pipework. Again, the graphic on the right shows a traditional DP orifice-based system. That requires a lot of upstream pipework, and that might not be suitable, for example, if I'm putting it offshore. But it might be perfectly suitable if I'm putting it in a field in the middle of England or Scotland somewhere. Clearly, downstream pipework, the same logic applies. But we also have to look at things like space above and below. Now, this might sound a bit crazy, but some of these things are heavy, and if things go wrong, they have to be lifted up to be taken out. They also have to be lifted to be put in the first place. And there is a world of difference between installing the system on the right in a field onshore, where effectively you have infinite space above. If I go offshore, and my metering deck is in the middle of 8 or 9 decks of process, then my space above and below, both for installation and for removal, is extremely limited. So again, something to bear in mind before you go and buy that Coriolis meter that's 10 foot tall. Will you get it in to the place where it's meant to go? And when it comes to calibration time, will you be able to get it back out? Removal, again, I've just mentioned that, folks. Most of these meters will have to undergo some sort of calibration. Very often, in the case of ultrasonic meters, Coriolis meters, EMF meters, that's done by removal and recalibration at a third-party facility, like the facilities we operate here at TÜV Süd in Glasgow. Other meters, like the orifice plate, for example, while they can be calibrated, or their uncertainty can be maintained without the need for removal. So there's a good example of where a solution which might not suit in terms of upstream and downstream pipework, the orifice plate, is actually at an advantage when we consider removal. So this is the type of balance that we're always having to try and maintain when we're selecting a meter. The weight, not a great consideration onshore, but a very important consideration onshore. And space for additional equipment. And we'll talk about that later, but that could be things like gas analyzers, for example, which that's the size of a small garage. Now, if you don't have space for that small garage for your analyzer system, then you're going to be struggling. I'm just checking my time. Okay. Now, additional equipment. I think it's hopefully I've made clear already that very often it requires more than just a flow meter to make a good flow measurement. There's a lot of additional equipment required, especially for systems which have to be multi-stream. We have to look at things like pressure and temperature transmitters. These are absolutely essential to give us the knowledge of pressure and temperature that we require in order to meet the stated uncertainties for low uncertainty systems, for high accuracy systems. They're absolutely essential. You can't just not have them. Densitometers. Very often we need to know the density of the fluid. And again, very often we can't get away from that. They do cost money. They do weigh a little bit. They do take up space. So they have to be considered. A meter prover, for those of you who work with crude oil or liquid measurements, you'll know that the prover is a kind of on-site calibration laboratory, a precisely known volume. If you want to have one there permanently, you need the space for it. You need to be able to handle the weight, and unfortunately, again, they're very, very costly. There's a lot of zeros at the end of the price of a compact prover. And even if you don't have a fixed compact prover, but you're bringing one in every 6 months or every year to verify the uncertainty of your meters, you still need to make sure there's space there. You can't just have it, floating in mid-air during your proving operations. So again, that's an additional equipment consideration which we have to consider. Valves and valve actuators. As soon as you have more than one stream, or even if you have one measurement stream, but you need to do maintenance, which is almost all the time, you're going to need some valves to divert the flow, to allow you to isolate lines. And the truth of the matter is, the inconvenient truth of the matter is, valves are heavy, valves are expensive, especially if they're made of some exotic material, and valves need maintained, and they weigh quite a lot. So again, this has to be borne in mind when we are making a meter selection decision. Inlet and outlet headers, you can see the pipework on the roof, if you like, of that metering skid, where the fluid comes in and the fluid goes out. This particular example is a crude oil, a viscous crude oil measurement skid. Again, they're heavy, they take up space, and if they're made of exotic materials, they're expensive. Sampling and mixing systems, very often it's well, not very often, it's almost always as important to know the properties of the fluid as well as the amount of the fluid. Now that means you're going to have to sample the fluid in the case of crude oil, or analyze the fluid in the case of, say, natural gas. And again, I know I'm labouring the point here, folks, but these items weigh, they cost, and they take up space. Even simple things like access ladders and walkways. There's no point in designing a metering system if the technician cannot get to the meter in order to do basic maintenance. So that increases the space that you need, it increases the weight, but you have to do that to make sure they have a safe working environment. And once we move away from the field, the actual hardware of the metering skid or the flow meter itself, the metering run, there's still more equipment that we have to consider. A typical metering system, whether it's, say, carbon dioxide or natural gas, will have dozens, if not hundreds, of signal and power wires. And all of that signal and power cabling has to be controlled. And that's normally done by having some sort of metering control panel, like the image shown there on the right. And that usually contains flow computers, purpose-designed hardware, which can take that information, pressure, temperature, flow rate, density, gas composition, valve position. It can take all that information together and allow the operator to control and take information from that system in a safe environment and in a user-friendly way. But again, to labour the point, they cost money, they weigh something, and they take up space. Gas analyzer systems, this is like the sampling and mixing systems we saw in the previous slide. If I want to know what's in my gas, and this is very important for physical measurement, and it's even more important for safety reasons. Is my gas corrosive? Is it going to knock me out if I breathe it in? It's usually a requirement, and this will be the same for carbon capture. I'm very sure it's going to be the exact same for carbon capture. You're going to need multiple analyzers running 24/7, so that you always know the properties of the gas, the composition of the gas, and the properties of the gas that is passing through your metering system, through your process. And again, you won't be surprised to hear me say that they cost money, they weigh a lot, and they take up space. So a lot to consider here that maybe wasn't initially considered when the question of go and get me a gas measurement or go and get me a fluid measurement solution was first asked. It can very quickly grow arms and legs, and very quickly the cost can escalate. It's maybe worth me pointing out at this point that another consideration, which isn't specifically detailed here, is doing the cost-benefit analysis between the capex of the system and the opex of the system. Very often, the system which costs the most to build and install may, after 10 years, be the one which was the cheapest to own in terms of total cost of ownership, because you built in low opex into the high capex design. And conversely, you may find that trying to save a few dollars on the capex after 20 years, you'll regret that decision because your opex has massively outweighed the capex of the initial system. Okay, we've talked about what's inside the pipe and what's needed to measure and analyze what's inside the pipe. Well, very often, or not very often, you should always, my mistake, always consider also the environmental or ambient conditions. And that's things like the ambient temperature, for example. You know, is this an LNG terminal in the Arctic Circle in Norway where everything could freeze up or ice up? Or is the equipment going to be installed very close to a flare line, which, if the flaring is happening, will bring the ambient temperature extremely high? I've actually been involved in work where occasionally the ambient temperature at the equipment got very close to or over the 55 degrees C rating for the equipment being used. That was never considered during the selection process. Again, the wind. Are you in a part of the world where it's very, very still? Or are you in a part of the world where it's very, very variable? For example, I'm thinking of the North Sea. One day can be calm, the next day can be a force 9 gale. In the summer, it can be 25 degrees, 30 degrees. In the winter, it can be -10, -15 with an unbelievably large wind chill. Well, that means you have to consider things like sunshades, thermal insulation for the pipe. All of these things are costly. You know, they have an associated cost. But if you don't do them, you'll impact the measurement. If you impact the measurement, you may not meet your required uncertainty. So again, it all has to be considered to make sure that the meters selected and the equipment selected is suitable for the environment in which it will be installed. Or if you can't do that, you can make the environment suitable. You can heat trace the pipes, you can cover the pipes in insulation, you can put air conditioning or heating in your analyzer shelter, but one way or the other, you have to make sure that the instruments are operated as they were designed to be operated. Humidity, again, is something for consideration. Sunlight, direct sunlight, can set up convection currents in pipes. At very low flows, that may actually impact the accuracy or the uncertainty of your measurement. Rain, yep, you know, you don't want to get stuff wet if it doesn't like being wet. Electromagnetic interference is not such a big thing now, I don't think. You know, we know how to earth and ground and install things properly, but you should really think about whether or not your meter is installed next to some massive big electrical transformer. For example, you know, outside a transformer room where there could be massive electromagnetic interference, and that could, you know, for example, impact on the ability of your electromagnetic flow meter to measure. Is it a hazardous area? Of course, this has to be considered. Is it zone 1? Is it zone 2? Does your equipment have to be intrinsically safe? Well, you know, you'll have that information available to you when you start your meter selection process, and you have to make sure that the meter you select and all the other instrumentation you select is suitable for that, that it's rated and installed so that it can operate in the area in which it's going to be installed without any additional hazard to personnel. And this is, you know, we've kind of gone through most of the main parts here, folks. So you know, we have a budget, which we've probably blown by now. If my experience, maybe that's just me being a poor engineer, but we usually got a budget which is no longer feasible. But keep referring back to the application and the budget and the reasons for the measurement. If you find something cannot be used, for example, you've got sand in the oil, well, forget turbine meters, forget PD meters. They're great meters, but they're not going to last very long in a gritty, abrasive fluid. So once it's out, it's out. You know, say goodbye, don't go back, don't look back. I seem to have missed a point there. Sorry, folks. Well, no, that's it. Once you've eliminated the easy ones, I apologise for that. I'm got the slides wrong in my head. You've got your requirements. You know your most important criteria. We've eliminated, as I just said, the non-suitable technologies. I've used the process, the physical and environmental conditions to narrow that list down. There'll never be one meter that's the best. Very unlikely. Never in my experience. and also, try and keep the budget and the application in mind at all times. If you have a custody transfer requirement of plus or minus 0.25% for liquid, well, that's very unlikely to be flexible. That's not going to be something that the commercial partners and the government regulators are going to let you away with. If you say, well, I couldn't spend that extra $50,000, so I'm going to give you 0.3%, not 0.25%. In my experience, that's unlikely to wash. You're not going to get away with that. So you just have to keep it in mind at all times. Then you review your final decision, and then you kind of list back to the start and say, okay, I'm going to use this meter, this analyzer, this material, these sizes. Go back and make sure. Does that meet my requirements? Am I satisfying my most important criteria? And you may have to go through this loop 2 or 3 times, maybe not. But that's, I think, folks, that's the kind of overview of the meter selection process. As I've alluded to a few times during the presentation, there's very unlikely to be one meter that will match all situations. You may have a choice of meters, you may need more than one type of meter, you may need more than one type of meter, but it's very unlikely that one meter will match all situations. Now, I will say that that's not always true. If I've got to measure, for example, let's say between, 300 litres per minute and 400 litres per minute of pure pentane, and it's a process that's very tightly controlled, and I want to measure the mass flow of that pentane. Just an example, or the pentane could be water. Well, a single Coriolis meter will do that. A single Coriolis meter will do that to a very, very low uncertainty. If, for example, I need to measure the volume of natural gas for loading an LNG tanker, and it goes from very, very low flows to very, very high flows, I'm going to need more than one meter. I could possibly use turbine meters. I could possibly use Coriolis meters, which are cryogenic, or ultrasonic meters, but I'm going to need more than one. I'm maybe going to need more than one type. So it's very, very, more often than not, there's not one meter which is the standout simple meter, because applications can be complex. Process conditions can be variable. As I mentioned, no one perfect meter for your application. If there was, there'd be no point in having this webinar, really. It would be self-explanatory. It would be simple, and in most cases you're going to have to compromise to get the uncertainty you want, because that's really, very rarely is that up for discussion in my experience. But the practicalities, you might want to put in an orifice plate, for example, because you don't want to send the meter for calibration, but you don't have enough space to put in an orifice plate. So you maybe want to put in a Coriolis meter there because it takes up less space, but you then need to remove that Coriolis meter for calibration, and that's going to be difficult. Or you're going to have to put in some sort of master meter in order to forego or minimize the calibrations, and again, that takes up more space, costs more money. So again, there's a lot of compromise here involved in getting to a good solution. And of course, the project budget. I keep saying that I was never much good at budget control, but you can't spend $1 million if you were given 10,000. So there's going to have to be some compromise. But if it's dealt with intelligently, and all the various aspects are taken into consideration, then more often than not it is possible. Okay, folks, just checking my time here. I think I've got another 10 minutes or so we should have time for a couple of questions. The meters that we're going to talk about here for these case studies are DP meters, differential pressure meters, orifice plates, turbine meters for liquid and gas, Coriolis, which are mass flow meters, inertial mass flow meters, I think they should be called, rather than Coriolis meters, but don't have time for that discussion today. And ultrasonic meters, which use high frequency sound and transit times. There are other ways, but normally it's transit times that are used to derive the volume flow, the velocity of the gas, and then the volume flow of the gas. So that's the meters that we're going to have in our case studies today. EMF meters are the final one. Very good for measuring conductive fluids. So as you can guess, there's going to be a water element to the case studies that are coming up in the following slides. Pardon me. So for case study number 1, we're going to look at a very common separator. This is obviously oil and gas related, but most oil and gas extraction points, whether they're onshore or offshore, will have a separator where multi-phase fluid comes in, oil, water and gas combined. It's separated by physical and chemical means, but mostly physical means. And then we measure the gas, the water and the oil coming out of the separator. So here's the meters we have. We have here's the process conditions we have. We have a flow range for the oil, water and gas, a Reynolds number, temperature, pressure, installation length, and there's required uncertainty. A little couple of comments there about, that may impact the selection of our meter. Now, what I'm going to say here is that what I'm going to propose as a solution is not necessarily the only correct solution, okay? There are probably other ways to do this, and if people think there are, that's great. I have no issue with that. But let's just walk through the selection process for this. So, what will I choose for the oil stream? I've got options of an EMF, a Coriolis, a PD meter, or a differential pressure meter. I've just realised I didn't mention the PD meter on the intro to this. As it turns out, it doesn't get used, so I think we're okay. Let's look at that. So the oil has a flow range of 10 to 1, turned in of 10 to 1. That's not particularly, difficult. The minimum Reynolds number is 200. That's very, very low. That's in the laminar flow region. Now that's not the easiest place to measure. The temperature's fine, room temperature. The pressure 60 bar. Well, it's high pressure. It's 20 times more pressure than there is in your car tyre, but it's not high pressure as far as offshore goes. We don't have much space to put it in, and we have a very low uncertainty requirement of 0.2%. There's a little comment there saying it may contain either water or gas carry under, i.e. the separator hasn't worked 100% and there is gas in the liquid. So the key sort of points there for me are the flow range, not too onerous. Reynolds number is low, and the installation space is limited. Uncertainty, that's a very, very low uncertainty. These are just figures for an example, ladies and gents, but they're not necessarily representative of real life. Well, if I look at that there, the PD meter I would never use because there's possibly a two-phase fluid, and I didn't explain how they work. Again, the DP meter, we don't have enough space. We've only got 5D. The fluid is unlikely to be conductive all the time, so I can't use an EMF. Kind of by a matter of elimination, I'm going to use a Coriolis for the oil. For the gas, let's assume we have the same 4 meters. I'll quickly look at the criteria for the gas. High Reynolds number. Rangeability is 20 to 1. There's a larger rangeability required. As I say, there's no problem with that. That's what we call turbulent flow. We've got plenty of space to put one in, and a reasonably low uncertainty requirement, but we need to minimize pressure drop. That's part of the criteria dictated by the rest of the process. So again, if I look at what's there available, well, I can't really see myself using a PD meter or a DP meter because they are introduce a pressure drop. But I've got plenty of space here, and I think that in that case, I'll go for the Coriolis meter. It meets the uncertainty requirement. Now, that's not to say, sorry, I'll go for the ultrasonic meter. That's not to say you can't use a Coriolis meter. You feel free, please do write in after this event, but please don't write in and say, why didn't you use a Coriolis meter? You probably could. But the pressure drop, depending on the sizing, the pressure drop may be why the ultrasonic meter is the best option. And then for the water stream, again, we've got the same 4 meters. We look at the turn down range, very, very large turn down range. No issue with the Reynolds number, it's turbulent. We have not really much space to go with, and a reasonably strict uncertainty requirement. It may contain oil or gas, but it's most likely to be the vast majority water. Well, again, you could use a Coriolis meter for that. There was no pressure drop. You could possibly use a PD or a DP meter, an orifice plate. But because they're quite cheap, and because they're low uncertainty, and because the fluid is conductive, I'm going to look for an EMF, an electromagnetic flow meter. But as I say, folks, it doesn't mean it's the only choice. I'm just giving this as an example. Literally a couple of slides left, and we should have time for questions. Just a quick case study. We're going to measure a corrosive fluid. Sorry for that. 20:1 turn down ratio, i.e. the maximum flow is 20 times greater than the minimum flow. The Reynolds number is 50,000 or above, so it's always turbulent. Temperature is quite high, 85 degrees C, and we've got loads and loads and loads of straight pipe. This is like a big pipe in the middle of a refinery. The choices I've got here are a Coriolis, a turbine, a DP meter, or a clamp-on ultrasonic meter. Well, we've got a corrosive flow. Okay, that's the key part of this case study. But we've also got 100 D of upstream straight pipe. Which meter would you choose? Well, for me, the meter that doesn't have to intrude into the flow at all, and because we have 100 D of straight pipe and therefore a fully developed flow profile, as in the Reynolds number is always in the turbulent range, for me, the most cost-effective solution there would be the clamp-on ultrasonic meter. Fantastic pieces of equipment. They can be installed without any interruption to the process. If they're properly installed, they give a good uncertainty. They don't have a pressure drop. Really, really good piece of equipment. So for me, primarily on a cost basis, I would use the clamp-on ultrasonic meter for that particular application. So in summary, folks, flow meter selection can be difficult. Sometimes it's really straightforward, sometimes it's not. Very often there is no perfect meter to choose. We generally have to compromise, but we just use that process of going through the environmental conditions, the fluid properties, the process conditions, the installation requirements, and the uncertainty requirements, and we just iterate our way down until we have the best solution for our particular application. And I can see from my preview that that's the last slide, folks. So I'm just going to say that if you want to get in touch with myself or John, please do so. John, thanks for still being awake, mate. And do you have any questions that have come in for me?
We've got a few questions, but I think before we go into the questions, Colin, is it probably worth mentioning the Global Flow Measurement Workshop that's coming up in October?
Absolutely, yeah. Absolutely, John. We have an event this October. I think it's in the third week of October.
22nd to 24th.
22nd to 24th in Aberdeen. It's the 42nd year that we've had our Global Flow Measurement Workshop. It used to be called the North Sea Flow Measurement Workshop. It's now changed its name. to the Global Flow Measurement Workshop in recognition of the fact that we now get papers from all over the world: North America, South America, the Middle East, the Far East, Europe, Africa. So it's the Global Flow Measurement Workshop. I'm lucky enough and honoured to be the chair of the event this year, a position I actually never thought I would have. And I don't think it's an exaggeration to say that it's the world's premier fluid flow measurement event. There are 3 days of presentations, workshops, breakout sessions given by literally the finest minds in flow measurement from around the world. The 6 sessions this year are single phase measurement, multi-phase measurement, emissions, carbon capture or carbon dioxide and storage and emissions, and digital. So we're talking about advances in computer science with flow measurement. We're talking about traditional energy sources, oil and gas, and we're talking about important environmental considerations, emissions, carbon capture, and future fuels like hydrogen. So 3 days of first-class papers. Attendance is normally in the hundreds. It's at the P&G Live in Aberdeen, and if you Google Global Flow Measurement Workshop 2024 or go to the TÜV SÜD website, you will be guided towards the web page. If you have any interest in flow measurement and the future direction of the flow measurement industry, I could not recommend strongly enough that you come along and join us at the P&G Live in October.
Absolutely. And I know from some of the people on this webinar today, there'll be a few faces that will be there, so make sure you come and say hello to us when you're there. Okay, we've got quite a lot of questions.
John and I will be there, probably around about the bar area somewhere.
We've got quite a few questions, so we'll try and fire through some of these, Colin. Okay. First one I've got here is, what type of meter should be used for highly variable oil flow? So I'm assuming from that they're talking about a high turn down ratio, a wide flow range. So what meter would you be looking at there?
If you're right, John, if we assume it's a highly variable flow rate, as in a large turn down ratio, the meters I would go for, and this might be the answer to quite a few questions actually, are a liquid ultrasonic meter or a Coriolis meter. And the differentiator there for me, so they both have very high turn down ratios, if they're calibrated well. If you're measuring the mass of the oil, you might want to go for a Coriolis if you can get it sized properly. If you're measuring the volume, then either the Coriolis or the ultrasonic. The ultrasonic could be used with a densitometer to measure the mass, but yeah, short answer, John, I would say highly variable oil flow, an ultrasonic or a Coriolis meter. You might need more than one, but they generally have higher turn down ratios than turbine meters, PD meters, or differential pressure devices.
Good. All right. Okay. What problems can limit the functioning of mass flow meters? So what kind of issues can limit the functioning of mass flow meters?
Okay, John. Okay, actually, I got a slight delay there in my feed, but I did get the question. For me, there's two types of problem. There's probably more than two, but two spring to mind, John. The first one, and I'm assuming that I'm going to talk about Coriolis meters for mass flow meters because I'm not really familiar with thermal mass meters, so I'm not in a position to comment. But if it is a Coriolis mass flow meter, installation problems, as in you orientate it the wrong way. It should be one way for gas, one way for liquid, another way for two-phase flow, to make sure that you give it the best chance of measuring. Also, if they're installed with any sort of mechanical strain, if they're squeezed or compressed or twisted, that can really badly impact the performance of a Coriolis mass flow meter. Process conditions, they can handle two-phase flow, but if your process conditions means that you have a two-phase flow, that can they won't be as good as they are in single phase flow. Solid contaminants, that can also have an impact. Again, it's an unwanted second phase, if you like. And one that I know from talking to my colleague, Dr. Chris Mills, here at TÜV SÜD, one of the world's leading authorities, if you like, in Coriolis meters, zeroing the meter. If you don't zero the Coriolis meter properly, it will not work as well as it should do. So installation problems, two-phase flow, and zeroing of the meter, I would say, are the main things that will impact the performance.
Okay. Well, I've got a general question here on, basically they've just asked custody metering best practices. I guess we can point them to the website for that one.
Yeah. There's a few things. Well, the first thing I'll say will be a salesman's answer, John. So you'll be quite proud of me. If you've got any issues with custody transfer metering best practices, feel free to get in touch. My email's on the screen. John and I will help you. We are expert. We have worked with custody transfer measurement over the decades in all world areas. There's a few things that help you. You follow the government regulations. You stick to the standards. You make sure you understand your uncertainty. Have a proper uncertainty budget done. Always make your maintenance a priority. Always keep traceability. But it is a difficult subject. So I'm not trying to be flippant here, but we do offer consultancy and training services in the area of custody transfer flow metering. So follow the rules. But if you're having any trouble, please get in touch, and we'll be more than happy to see if we can help you.
Yeah. Okay. And I think at that, with a couple of minutes left, I think we'll just call it quits at that, Colin. Thanks again for joining us. As I mentioned earlier, you will receive a link to a recording for today's presentation. Please get in touch with us if there's any webinar subjects that you would like us to cover. It's always good to hear exactly what you're interested in. Feel free to get in touch with myself or Colin. As we said, you can send any queries to info.uk@tuvsud.com. Also visit our website, www.tuvsud.com/UK, for more information. You can also book the Global Flow Measurement Workshop by visiting our website. And on behalf of myself and Colin, thanks for joining us, and have a great day.